Okay, welcome back, everyone. So in this talk, I will be continuing on the things that Rafael presented a few minutes ago and put some numbers on, based on a few experiments that we have been doing. My motivation for this talk is that every time we go to a conference and discuss how we use async packing for hybrid Intel processors, we get the question on why are not you using EAS or why are not using CPU capacity. So I wanted to give it a try and present some results, not on full EAS, but on the capacity calculation side of things. First, I should take a few seconds to acknowledge and thank the people in the slide who contributed to some way or another. Some people made tools for me to do this presentation, some other implemented trace points, such as Rafael wrote a few patches that I come to discuss here, and other people give feedback on it. So in this presentation, I will discuss an experiment in which we we use a user space tool, which is similar to RT app, which is Yogini, in which we request a certain amount of work from the CPU. You see at the top plot on the screen, that is the work amount, the amount of work that we are requesting from the CPU, based on being 100% the work that the biggest CPU on the machine can achieve, meaning that at this point we are requesting 100% of the work, and as time elapses, we request less and less work in the definite chunks of time, meaning that when in a chunk of time, if the CPU has completed the work we ask, the CPU goes silent. And then we compare that, the requested amount of work, on what we've actually achieved. And in this plot here, we have two types of CPU. This is an Alder Lake S system, where the red line is the P core, which is the big core in the system, and the blue line is the E core. So in the red line, we see that is the biggest CPU, and therefore it should be able to achieve the 100% of the work that we requested. And we can see here clearly, because the line follows closely the shape and size of the line at the top of the screen. Whereas on the P core, we see that for certain portions of the plot, we see that the E core cannot achieve that amount of work, and therefore it can achieve only 60% of the work that the P core can achieve. So there we.
If you can please elaborate, explain. So we have percentage of the requested work. Can you say, what does that mean? Like, are you asking certain, I don't know, arithmetic operation, and the CPU doesn't do that? Like, I don't.
Yeah, that's a good point. We can request several types of work. In this work, what we are doing essentially is going in a loop and running, in this particular case, get CPU over and over and over and over and over.
Get CPU, right.
But we can change that for other types of work.
And what does it mean that the blue line gives you 55 of the work you ask? It answers you 55% of it. No, it means that it does less calls in the fixed amount of time.
Yes.
Is that correct?
Mm-hmm. Yeah. We asked it to, let's say, 100 units of work, but it was only able to complete 60 units.
So it's a certain number of get CPU calls, and then the percentage is the number executed divided by the number,
the max number,
the number that you wanted, and also I wanted to add to it that the frequency and idle time are free variables to it. So we allow the processor to adjust to the amount of work given to it.
Yeah, that's correct. We are using hardware controlled states. So the hardware decides how to scale frequency to complete the work that we request. So how does that look today in the kernel? The experiment that I made was on the mainline 6.9 kernel. And this is how it looks like. As I said, frequency is a free variable. So on the top plot, we see the work, the amount of achieved work that we get and how that maps to frequency. We can see that the P-core is able to run at higher frequencies, and the P-core it's only able to get to this amount of frequency, which is 3.8 gigahertz. But as we request less work from the CPU, the hardware decides that it can now run at lower frequencies. That's that we observe here. And now on idle time,
it's with Intel P state HWP.
Yeah. And now on idle time, as I said, for every chunk of time in which we request some amount of work, the CPU completes the work that we requested and it goes idle if it completed earlier. And the observation on that on idle time is that when we are requesting a lot of work, the E-core is saturated, meaning that it can barely cope with the work that we requested. But the P-core is able to complete the work and then go to sleep. That is why we have more idle time on the E-core as we increase the amount of work. Another thing to observe here is that when the E-core can cope with the requested amount of work, we observe that it has less idle time, meaning what we can observe here is the architectural differences between the E-core things such as IPC ratio or cache topologies. We can observe that it spends less time idle than the P-core for the same amount of work. And now, how does that look in the scheduler? What we observe here is, again, the achieved amount of work and how the utilization in the scheduler look like. So if we want to do things such as EAS or capacity-aware scheduling, the first thing that we need is to have a frequency and CPU invariant signals. But what we observe here in the mainline kernel is that we don't get that. This is also a requirement to use things such as the schedule governor. We cannot use it effectively if the utilization of the same task is a number on the P-core and a different number on the E-core. And that is definitely not the case. It's definitely the case here. We see different utilization numbers. And
just if you go back to this one, okay. Because I mean, if you look at that, it looks like for your E-core, for the same amount of work, you're effectively running longer. So, okay, yeah, the utilization is higher. And in your next slide,
so this
you are using the same. You're considering that you have the same IPC for both core.
Well, so this includes the current frequency invariance code.
Okay, but only the frequency, not the fact that you're not using maybe the same micro.
Yeah, just the frequency, and actually it is off. I think that Ricardo is going to talk about it.
Yeah, in this next section, I will discuss how does that look like when we use async capacity.
As far as one quick question, as far as the reason for using the starting at the high ramp or the high amount of work and then requesting less and less work over time, is that something to protect from thermal numbers coming into effect here?
Yes, yeah, because if we started from low to high, by the time we get high, we may have reached some thermal or power limit. Yeah. So this is for simplicity. Yeah, I forgot to mention that this is a very simple experiment. Maybe it's not a real world example, but it is simple enough for us to understand the behavior of the software and the hardware. And what I'm presenting here is two types of work. The examples that I use here is running the same loop of requesting certain amount of work, but this time I'm using VNNI instructions. And on Alder Lake, I select this type of work because on Alder Lake, these VNNI instructions have a rather high IPC ratio as compared with the E-cores, but that is not the case with other types of instructions in the system. So we can see a very distinct difference here. You can see that the gap between the utilization on the VNNI case and the gate CPU case is bigger, meaning that invariance needs to be done not only on frequency and CPU type, but we maybe even consider an extra dimension, which is the type of work that it's put to do on the CPUs. Yeah, so probably everyone here in the audience is aware of this, that in order for use things such as EAS and capacity, we need to scale on frequency and we need to scale on CPU type, the microarchitecture of the CPUs, which is done here. Just pay attention to the yellow box indicating that we do those two scaling factors. Now going to the async capacity case, I experimented with patches that Rafael posted on LKML recently. This is the link and the QR code. If you cannot copy or type fast enough, you can use the QR code for that. For this, we enable asymmetric CPU capacity on x86 using the hardware p-states capability information that we get from hardware. And from there, we get the number that we use to fit async capacity is the highest performance value of it. This is not a guaranteed value, but it is whatever maximum performance a given CPU can give. This is a per CPU number, and we use to fit that for each CPU.
There is separately. A small typo. It should be highest per. But other than this.
Oh yeah, that's yeah. Yeah, sorry. Yeah, there is a typo here. And the other thing that I wanted to mention here is that this highest number includes an IPC scaling factor between E-core and P-core, as well as the max frequency in which the both CPUs can reach.
Question: this highest perf number, is it what is the unity, the measure of it? Is it the hertz, or is it an abstract number that represents some quantity? Is it frequency? Is it?
No, it's an abstract number. Yeah. So yeah, but yeah.
When I tried this, I also asked in the patch set, the number I get on the hybrid system I have, they are the same as the number of the IPC class 0. Mm-hmm. And so the question was for me I'm not sure, are the IPC classes, is class 0, is this like the default class, or is it like, because I was wondering why this information is per default class, right? Because it doesn't have any class notion. But when I look into the what's called HWI or no date HFI classes, then this represents class 0. Is class 0 the default?
Yeah, in the generations of HFI, the first generation only had one class, and then it got extended to classes of work. And I'd say that I would call it the default class. but I will not assume that it is going to be the case always.
Right. So I don't think that there is any guarantee on the relationship between HWP cap numbers and HFI classes.
I was just wondering the numbers.
Because it will, okay, whatever, no guarantees.
Okay, so that is how we achieve how we fit large scale CPU capacity, which is a good thing, I think, because if we look at the definition of large scale CPU capacity, it considers the max performance of a CPU at max frequency, including whatever microarchitecture's properties it has. So yeah, that's a happy thing. This is how it looks. The utilization looks when we implement the capacity scaling of utilization. We see that previously we had the utilization over here, but now it is under here. So we scale it down too much, but at least now we see that it is more, that is a bigger overlap between the E core and the P core. And this is how the capacity looks when plotting after these changes. We see that the P core is now the 1024 max capacity of the CPU, and the E core has a capacity of maybe 600, I'd say. But there is but when we look at how that capacity is scaled in frequency, we see that the P core is correctly on the 1024 line. However, we see that after scaling for frequency, the capacity now it is under 500, whereas it should have been over 600. And the reason for this is that we are not doing the frequency scaling correctly on hybrid processors. And here is the reason here. Again, in our work example, we see that the frequency scaling factor is correct for the P core. Well, not exactly correct, but more on that in a minute. However, on the E core, we see that this line should, if we had correct frequency scaling, the blue line should also be on the 1024 limit when we run at max capacity. However, we see that it is maybe on 800. So we are underestimating the frequency scaling of the E cores. And again, another problem with the only scaling CPU capacity is that, again, if we do different types of work, we see that sometimes it overlaps correctly for a certain type of work, but for other types of work it doesn't overlap, which again is one more confirmation that probably it is a good idea to also make invariance based on type of work. Yeah, so now jumping to the topic of frequency scaling. This is how frequency scaling invariance is done today on x86. The important things to remember here is that this turbo-freq ratio, arc turbo-freq ratio, is a single number for all the CPUs in the system, which is not correct for hybrid platforms, given that the E cores and the P cores have different max frequency. And the way in which it is calculated is taking some some number for max frequency, which what we take is from this register the max turbo ratio that we get when 4 cores are active at the same time. And for the base frequency, we take this number here, which for this ratio means that we can assume that it is the max frequency ratio that we should use for frequency scaling. And after doing all this math, we arrive to the number that we use for frequency. Then the factor that we should use for frequency scaling gets us to this number, which is the minimum of 1024 versus the turbo ratio multiplied by the changes in these registers. Just for general information, we use these registers, which are essentially counters that count. Yeah, it's an account of that. Yeah, obviously changes in time, but the difference between these two is that M-perf increases at a constant rate, whereas A-perf increases faster or slower depending on the performance state of the CPU. How these numbers look when we do this on a hybrid core. This is just the formula that we got in the previous slide, but I fed numbers in it. This is the four-core turbo number that we get from the turbo register, and this is the base frequency number that we get from the platform import register. I don't want to say these are frequencies; these are just numbers.
Yeah. So this is for a specific system, right?
Yes.
It can vary from one system to another, and this is for a specific system.
Exactly. This is the machine that I use for the experiment, which is another lake system. And now, if we were to examine what is the behavior of this scaling when running at max frequency, it will look like this. So meaning that if the A-perf counter were counting at a rate of 5.1 gigahertz, and the base frequency for the ratio will be 2.5 gigahertz, and we do this math, we will see that the frequency scaling of the P-core can go from 0 to 1066. So we see that with the existing code overestimates the frequency scaling by maybe 5%, and that is acceptable. That works well enough for cores. That is the reason this code works on non-hybrid systems reasonably well. But if you look at how the E-core looks, again, we feed the numbers of the hardware into the formula, we see that the max frequency of the E-core is 3.8 gigahertz. That meaning that the A-perf counter may be increasing at that rate. And we, after doing the math, we see that the frequency scaling factor that we use for our calculations go from 0 to 775, meaning that we are underestimating the frequency scaling of the E-core by maybe 30%.
Yes, I wanted to comment on this part for the benefit of the rest of the audience, also to retell the lore of how those numbers were selected.
Yeah.
I haven't followed all the changes since then, but in 2019, when it was suggested to me that the 4-core turbo as a fantasy assumption of what could be the maximum frequency was good enough.
Yeah.
Paul Turner said it was an OSPM, and Paul Turner said, why don't you use 4-core turbo? I said, why not? And so actually tried several possibilities for guessing max frequency and ran benchmarks on it, and the one that won more benchmarks, 4-core turbo, put that into the code. So for again recalling how this went. and that was a patch that I recycled from Zelstra, who brought it initially. Now, the content of this slide, what I'm seeing here, and I believe you have a point at which you are arriving in the next slide or something, but those are a maximum frequency, and a maximum frequency, that number, arch tract scale, should be 1 or 10 to the 4.
Yes.
This is what should be. So what if everything was perfect in those slides? We would have P-core 1024, which in fixed point arithmetic means 1 with the 3 significant digit, and E-core 1024, which again is 1, because we are at maximum frequency, maximum capacity, which is 1.
Exactly.
Now this is not happening because I just, as I just told you, the maximum frequency, I pull it out of a magic hat, or I made it up. Okay. But in 2019, only P-core existed.
Yes.
And now you say, well, but now we have P-core and E-core,
exactly.
And these numbers that you made up is even nonsensical, because maybe it's close to truth for P-cores, but it's nowhere near meaningful for E-core. And this is why E-core, instead of having 1, it has a 0.7.
Yeah.
And so this is, I'm waiting for the point, essentially, because of course this is not going to work for hybrid. It was never meant to, you know. So
yeah, that is the reason I said that for P-cores this code works reasonably well. And I look at even for this platform, I saw the value of the 4-core turbo ratio and the 1-core turbo ratio is not that much difference. So meaning that it was reasonably well for P-core.
But the base frequency. So the 4-core turbo is, there are 2 problems with it. So first of all, is 4-core turbo, which is kind of the matter of of discussion by itself. But the other problem is that we take those numbers from a boot CPU, which is of a specific type, like a P-core, for example, and we use it for all the CPUs, which is a mistake, right?
Yeah.
Because
but the turbo ratio register is a per package register, right? So it is the 4-core turbo ratio, but my point is that what you get from the turbo ratio register may not be true for what we get from HWP.
Let me present. I now forming my thought in a more articulate way, and what I really want to say is, in 2019, the number that I made up was 4-core turbo, but base frequency was correct. Now, with E-core, not only max capacity is made up, but base frequency is also wrong. It's wrong. They don't have 2.4 gigahertz at base frequency. Is that correct? They don't have it.
Yeah, well, this made my numbers work, but you're right. It is not trivial to know from where to get these two. The number of this arithmetic.
The difficult part at the time was what is the max? Know the base. But now you don't even know the base. Or I believe you do, but it's in a different MSR. That is a specification.
Exactly. That is what is running trouble, from where to fit this math to make things work.
But if you don't know, nobody knows. I mean, it's where the nominal frequency, the base frequency of an E-core. Can you get it from anywhere? I hope so. Wait. Okay, there's the point. I just wanted to highlight.
All what you said is true, and I run onto the same troubles. Sorry. So what I did for the sake of this presentation is just get whatever numbers I could from the hardware and plug them into the kernel in a very hacky way to just to see if it works or not. And this is a repetition of what I just showed, so I will just skip that. But now, yes, it's the same repetition. What happened? Yes. I don't know what happened there, but this is how the frequency scaling looks when using the correct numbers, quote unquote. for the frequency scaling. Now we see that the Arch CPU scale capacity is in 600. And after correcting for frequency, we see that at max frequency on the E-cores, we still get the 600, which is what we want for a correct frequency scaling for different types of CPU.
And the correct numbers, they were 1066 and 775, or those were the correct numbers, or right?
Those numbers were
Once Dietmar asked the ground truth numbers were 1066 and 775. No, those are gross overestimate. Those are mistakes. They come out of.
It has to be one number.
They had to be one. They were expected.
I just remembered we had in ARM, we had those big little systems just based on frequency ranges. And we relate all the frequency things towards the max CPU frequency in the system, not on the CPU, right?
We have the range 0, 10, 24. Okay. So for each CPU, the frequency capacity is going from 0 to 1024.
But then we changed it in the meantime because we had those big little system based on frequency only. I don't know.
Maybe, but
okay,
at least
cool.
right now it's that
okay,
it's the range is for the CPU.
Oh, yeah. Yeah.
To Dietmar.
Yeah.
Sorry, Ricardo is telling the algorithm that the E-core, the small core, has base frequency, which is the nominal peak, the max non-turbo frequency, the same of the P-core, which is not true. I think it's not true.
Yeah.
It goes slower. So you see what I mean? So
yeah.
like it can work. I don't understand.
Yeah. So this is how I gather it works to the best of my knowledge on ARM, which is essentially the same as an x86. We have a delta count of some registers plus some max frequency that they get from somewhere. However, the difference is that in ARM, you use a per CPU max frequency, which is what we wanted to do in x86. And the max rate you get from CPPT information. I am not sure if the max rate is different for CPU or not, but the point is that the only difference between x86 and ARM at this point is that ARM uses a per CPU max frequency, which is what we also would like to have for x86.
Because Arch scale CPU capacity is used in different places for different things. If you feed it the same value that you feed into it has also needs to be used in Arch max freq scale computation, because otherwise you get inconsistent.
Yeah. So going back to the 775. So in this plot, what we see is the Arch scale capacity that we get from the constant microarchitectural capacity of the CPUs, which in our experiment was 1024 and 600 for my hardware. And the 775 that we saw here is the underestimation that we have. This should be 1024, not 775. And yeah, so now it looks better. And when you look at how the utilization looks after scaling for capacity and scaling for frequency correctly, the utilization overlaps in these types of work, which is one CPU, and this is some math work. So it looks much better than in the beginning of the presentation and the middle of the presentation.
And to get those plots, how did you plug the correct numbers into the formula? Did you hard code them to run the experiment? Of course. You didn't gather them from the MSR. No. You say, okay, this is got to be 37, 37.
Yes, I typed those numbers. Yeah. And I will go to that in a minute. And again, going back to the type of work thing, even after doing all these things, if you have different types of work, the utilization may not be correct for certain workloads. Going back to the extreme example in Alder Lake, which is the NNI, you start to, because the IPC ratio is so big in this platform in particular, VNNI work is not completely CPU invariant. And so yeah, I had those numbers, and now I started to discussing and seeing from where I could get those numbers, but there is not an easy answer that I could get. So Rafael was suggesting to use the ratio between highest and HWP highest performance versus guaranteed performance. I tried that, but it didn't work. Maybe I didn't do it well enough or didn't do it correctly, but that didn't work for me. And even the guaranteed performance in HWP can change if we change if the conditions of the system change over time, maybe if you reach some limit. So what I would like to have is some numbers that don't change, or I can assume they don't change, or they will not affect our arithmetic when doing this invariance scaling.
In principle, there is nominal performance in CPPC that should be the performance, because what you need is a frequency at which the ampere counter is ticking, right?
Yeah.
But that should correspond to nominal performance in CPPC. However, that number comes from the firmware, and it may or may not be
exactly
correct.
Yeah, that's another level of complexity. Yeah, actually, when I said I hacked those numbers, I didn't exactly type 3 and 7. What I did was take highest perf and nominal frequency, nominal frequency from CPPC. So yeah.
It's nominal perf. So I still think that I would still use guaranteed, and that because that comes from, at least from the microcode, and not from the platform firmware.
Right. Yeah, of course, if this can break down if the hardware is not giving you the firmware is not giving you the right information.
I wanted to try explain Intel how to design a chip, which I cannot do in any degree of authority. Okay, I'm just but on AMD, this particular value is not gotten from an MSR, but from ACPI tables. So is there any chance that you can convince, because the ACPI tables, that you don't write them, it's the OEM who writes them. Okay, so you don't trust.
Yeah, so again, that exposes to risk of some hardware somewhere
it's
not
the same
having
problem.
tables correctly. So I am done actually. So that is the biggest open in this presentation is from where to get the numbers to plug into the math of frequency scaling. Okay, so Rafael has the answer. Okay, so that's it.